Okay. Are the slides visible?
Yes, ma'am.
Okay. So I have shared a link with all of you based on some basics on embedded system and embedded processor. Have you gone through the link? Yes, no? Is there anybody who have not gone through the link?
Ma'am, when did you share it?
In the chat I have shared.
Okay.
Yes, it was there, right? Wait, let me check. Yes, you can see I have shared on 26th. So others, so that it seems you have not gone through the link. Who asked the question?
Me, Yash Agarwal.
Yes, okay. So about others, so you're from which background? Yes,
Ma'am, electronics and electrical communication.
electronics. So maybe you have some background with embedded processor, right?
Ma'am, I'm a second year sophomore, but I do
Oh,
have some.
second year. Okay.
I do have a
Okay.
background of embedded processors.
Okay.
Uh,
So for others,
Ma'am, the link is not visible. Can you please once repost the link on the chat?
it's not visible. Okay. Here I can see on 26th I have shared. Okay, I'm reposting. How to repost? I'm just copying it. Reshare. Is there any option? I can see any option. So I'm again copying it. Okay. This is one and this is the second one. So nobody has seen the link. Is there anybody who has gone through the link?
Yes, ma'am.
Anybody? Yes? Nobody? Hello? Can you hear me? Hello?
Yes, ma'am, you're audible.
So nobody has gone through the link. That is the point, right? No, yes. Good. Please go through the link. I have shared it again. Okay. So because that will today I will discuss something. Of course, today also I will discuss about embedded processor. Why I am telling you to go through the link, because today we are going to discuss about this processor choice. Like so far we have talked about the basic blocks of CNN, and what are the operations required to implement the blocks. Now we have some idea. We have the idea how the convolution layer, that how it looks like. What about pooling? What about this ReLU, Max, etc. So that we have. Now we are going to choose what type of processor will be suitable for this type of operation. So for that, since you have not gone through the link, so I had planned today to start with this example, where we are going to talk about one embedded ML application, that is, this is intelligent hearing assistive device. So what is the concept? Like in case of speech enhancement, we know about that hearing aids, right? Hearing aid devices. So that is basically works on the a concept of speech enhancement technique. That means you have some speech related signal, you are enhancing that, and you are passing that through some speaker. And based on that, on these concepts, we generally develop these type of speech, hearing aids, hearing assistive devices, etc. So when we are talking about this word intelligent hearing assistive device, what is the concept? We are actually adding this machine learning concept to it. That means initially we are talking about some processor which was taking this signal, noise based, a speech signal with some noise. It's used to amplify the actual noise in some way, and then it used to give output to the speaker. But now we are actually making it intelligent, where we are embedding some CNN block. That means based on some learning concept, we are checking what type of noise, what amount of noise we have to mask based on typical types of inputs. So now we have some set of input signals, and based on that, your intelligent hearing assistive device will be capable enough to mask some amount of noise, and that way it will send the output that we constructed speech to the it will output that as the output of your this smart hearing assistive device or smart hearing aid. Okay, that was the example we were about to take. Now you understand this is one typical example of embedded machine learning device where we are actually using machine learning, but in embedded context, because this hearing aid, of course, there you cannot within that hearing aid device you cannot support huge processors, huge servers, and to with them with together adding them up all, you cannot process the CNN. Here you have to work, this hearing aid is very small and you have to work in a very resource constrained scenario, and that's why embedded processor is coming into picture. General purpose processor will not hold good. Okay, so just since I will come in detail about what is the mapping of the CNN and then what type of processor I'm going to choose, before that I'm just, since you have not gone through the link, I'm just giving you a brief idea about three concepts. Okay, one is the general purpose processor. When we are talking about processor means what? I have to do some computation. For that I have some related data, and what I'm going to do, that is my instruction. So that data and that instruction, that data and instruction is stored somewhere. We are terming them as memory. Okay. From this memory, you have some control unit input. That means some control will tell that, okay, now I'm going to feed some data from this memory unit. Now that memory, that data will go to some arithmetic logic unit. We term them as ALU. Okay. Now arithmetic logic unit means nothing but some adder, subtractor, multiplier, etc. Different modules are there, different blocks are there present in this arithmetic logic unit. That means this arithmetic logic unit is supporting you the basic hardware. That hardware, when you give input some data from this memory block, that hardware will work accordingly and give you some output. Let's say you are giving some data 1 and data 2 and you are passing that to ALU and this ALU is giving the output. Okay. Now that output may be going to some IO device. Okay. IO device. Before that, now I talked about some control unit. These are control units. Control inputs. That means there is some control unit. This control unit is giving the control inputs to this data or instruction memory from where you are fetching data on what to do, that is the instruction, and on top of which value you have to do it. Addition on top of which value, subtraction on top of which value. So that instruction will be stored in this memory and control unit select according to your requirement. This control unit will select those values from this data or instruction memory. Okay. In some cases, this data and instruction memory, like the way I have drawn, those are fused. And some cases we have separate. One is one is data memory and one is instruction memory. So when these are separate and together they are forming your memory part. So maybe based on that, whether your data memory and instruction memory is fused or they are separate, based on that we term them in terms of some architecture. One is called Harvard architecture, one is called one-in-one architecture. So these things, this basic idea you will get from those that recorded lecture. So that's why I told that go through that. It will give you the idea of very basic blocks, nothing else. Because typical very important features of embedded processors, and those are meaningful especially for this ML implementation, we will discuss here, no problem. But these basic terms, basic architecture, basic blocks, you should get some idea about it. So please, today it is fine, but please, if possible, go through it today after the class and come tomorrow after listening that lecture. Okay. And from this control unit also, this control unit provides the input to ALU and to say that, okay, now I'm enabling, maybe there are adder, as I told, adder, subtractor. So when your instruction is instructing to do some addition, it is basically enabling this adder unit so that this output will come from this adder unit. Okay. So basically, these are the basic blocks: memory, control unit, ALU, IO. These are the basic blocks, and together they form the processor. Okay. And in that lecture, there is one very nice example. It is showing when you are writing any C code, step by step, one GCD example is given. When you are just, I hope all of you have written such type of C code, C examples. Whenever you are writing that, you are executing that in any processor, how that your software code is getting mapped to your underlying processor, to this underlying ALU block. So that step is shown here. It was shown in that lecture. So please go through that. Okay. So this is the basic idea of processor. Now, when we are talking about processor, there are three types of processors in general. So number one is general purpose processor. That you will see in that example, in that recorded lecture. There you will see whenever we are talking this ALU is composed of multiple blocks, adder, subtractor, multiply, comparator. And think about your normal CPU or your normal any high-end server. There, the processors are with this type of very general purpose. That means multiple types of operations, multiple types of programs you can actually execute. And for that, whatever hardware needed, it is included in that type of processor. Okay. Another type of processor is application specific. Okay, application specific. Now, for this type of processor, what will happen? This is very application specific. Let's say, as we have taken the example of maybe some very small application. Also, there we will get the definition of embedded devices or embedded applications, which says these embedded applications, when we are talking about embedded applications, they are not very much related to multiple objectives. No, they are very specific to a single objective. Okay, single objective. Most probably this part we have talked in the previous class also. So when we are talking about single embedded processor, we are talking about very single objective processor. So for that means maybe for that we just need the adder or just need the subtractor. That's all. It is not required to have everything in this ALU. Okay. So ALU processor is very much application specific, where a particular certain domain of for a single application or a certain domain of application, whatever basic blocks required, only those are supported in this ALU. So if you want to do a very complex operation, you may not able to do that, implement that in that application specific processor, because that basic modules, maybe those are not present there. So that way, application specific processor, it is very much suitable for embedded scenario, right? So is it clear so far? Now here, if you see that discussion, the example it was taken, like the GCG computation, a very typical C code example, it is intended for that general purpose processor. Okay, but whenever whoever has done that embedded software design validation or those type of courses, you will see there we mostly talk about embedded computation or embedded applications. There also, processor is not so general with this as general as we consider it in general purpose processor, because the basic reason is that when we are actually considering the huge ALU, huge adder, huge subtractor, multiply, or other supporting other blocks supporting other complex operations, of course the area for this ALU is increasing, and in that way it may not be suitable for an embedded application, because that huge ALU you may not support in your, you may not consider when you are actually designing some resource constrained embedded application. So due to its resource constrained nature for this embedded application, these application specific processors are very much suitable. Okay, so this is the first thing. The second thing is that when we are moving to this, this is about not only about ALU. This is true for IO. This is true for data and instruction memory, because when we are talking about general purpose processor, maybe we are thinking about some kind of parallel processing. There we are actually executing multiple programs. That means huge amount of data we have to store, huge amount of instructions we have to store. But for in case of embedded application, since we are having single objective, single application is running on that embedded processor, then we do not need that. Okay. So this processor technology is a huge field, and there are different types of processor based on different types of customizations available. In this today's class, we are mostly going to discuss about one particular type of application specific processor, that is DSP processor. Okay, because this DSP, this is one embedded processor, this is one application specific processor, but it has some typical features, and that features will help us to actually improve our to implement that CNN requirements efficiently. So that's why in this class, for this course, we will mostly focus on these type of DSP processors. So that it will be low cost, it will be low area, it requires low resources, and it has some extra features that we will be discussing today. That will be useful for our this type of CNN, especially this convolution. You know that when we have discussed last day, we were mentioning that this convolution is the most costly part. So we will be focusing again and again to that convolution part, and we will see how we can implement that in this embedded processor. Now first we will explain. That's why what I am telling that today I will be focusing on discussing on this typical embedded processor. But what are the other options you have? Okay, to know that, please go through that lecture. That will make you. I hope that will be important to clear your understanding. Okay, next, come back to this example. So we were talking about this intelligent hearing assistive devices. Now you mostly understood that we already mentioned that what this assistive devices they do, they receive some speech signal, then they convert that to some analog to digital converter through some ADC converter. Sorry, so through some ADC, and then there is some DSP processes required to perform this speech enhancement. Okay. Now this DSP processor we are already using. It is nothing that, see, when you are actually thinking about applying some extra optimization or improvement, you have to think what you have in hand, or in other words, whether the optimization or the extra solution, whatever you are providing, whether your system, the other requirements of your system are capable to accept that or not. So the basic idea is that whenever we have beforehand we have designed this hearing assistive devices, we were already using this DSP processors for this speech enhancement. Okay. Then in this context, when we are talking about this CNN, we will see what are the basic a few features of this DSP processor that will also help to realize this CNN efficiently. So we can, in a nice way, we can actually map this CNN requirements to this DSP processor. Okay. So that is written that recently neural network based speech enhancement algorithms demonstrating a better performance. So what are the steps of this NN based algorithm? That is, a model is trained for speech enhancement using noisy speech data as the model input, and the target is to get the clean speech data. Studies first transform speech data into a spectrogram. So we have the spectrogram. Let's consider some form of signals. If you are not, for other than maybe electrical and those type of domains, this spectrogram we are not very much habituated with. We will think that some form of signal, some form of input. For processing, since speech primarily consists of some frequency domain features. Okay. So this is your input spectrogram. Consider that as other general input to your convolution layer, and then from there you are getting the feature map, and to do that you have to do you have to pass that costly multiplication related to your convolution. Then you have this pulling layer, then you have this fully connected layer. I think this part we have already discussed a bit. We know why we need this. Now, when we have this feature map, and we know that on top of that, we have to do this kind of operations. We will be having some weights. That weights will be coming from our filters, and we have to do some this kind of multiplication operations with this coming from the this feature values and coming from this filter values. Okay, so we are just dividing this feature map into different frames. Now after that, we will come to the left side later. After that, what we are doing, these are our input frames, and with that we have some weight values, and we are doing some multiplication, and basically we are trying to do these type of implementing this type of functionality, F into W, and we know that this is the most costly part, this multiplication. After that, we have different type of activation, and well, to implement them, it is not so that activation function implementation, that is not so costly. So this is my costly part, and I have to find some processor, that is my objective, where these costly parts can be implemented most efficiently. So whenever we are choosing, this is one application. The image is not where someone maybe asks, I have seen in the chat, that what other than speech processing. Of course, we will one step by step. We will, don't worry, we will take different examples, and there we will see not only for speech processing. There are multiple examples we will discuss one by one in different scenarios. For this case, when we are talking about this computation, we have to check this type of multiplication and then so multiply and add. That is the basic function, right? Is it clear to everybody? Just stop me, okay, if you have any question, because I can't see you, so sometimes I get confused. So this is so if my main objective is to choose some processor or choose design some processor, maybe in some cases, yes, in some cases it is like when we are designing application specific integrated processor. One second, just a second. Hello, sir. Yes, 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 yes. Sorry. Okay. So to do that, to implement that multiplication efficiently, we can see that is very much analogous to what we have in our existing DSP processors. Okay. In case of signal processing, we know that FFT or this type of DFT based multiplication computation is very common. Those who know that, is good. Those who doesn't know that, still it is fine, doesn't matter. Just you focus on the type of algorithm we are we are talking about. We are talking about this DFT or FFT computation. You may not know. We are not going to discuss here why this FFT or DFT is important. But the important part is this part. If you observe this part, you can see it is again have some requirement of implementing some multiplication and then some additive feature. That means here, if you see, if this is the some input and this is some output, we require to do this type of FFT computation. What we do, we have this type of some factor value and some input. We need to have this multiplication and this summation. Multiply and add. the same requirement is always present, and there's a huge literature where we actually try to exploit different type of processor technologies, and we try to investigate how we can actually improve this kind of applications or this type of algorithms in terms of implementation. So that's why these two are very much analogous. And whatever we are going to discuss is that the types of processors, they're supporting this type of signal processing function. They are very much suitable and they are effective to improve the convolution requirement for convolution and this type of performance in case of machine learning or this CNN or this type of deep learning scenario. Okay. So with this motivation, we are actually, if someone, doesn't know at all about this, how this FFT or DFT algorithmic structure looks like, you just focus on this part. It is already having this type of multiply and accumulate, multiply and add, this type of structure. So this is very much similar to what we required in CNN computation. And this is the main objective that we are going to discuss in this class about this DSP processor. This is a specific type of embedded processor, and we are going to discuss some features of this processor, and that will be meaningful to implement our this ML concept. Okay, something it is given that you have to do this multiply and with this is called this twiddle factor computation in FFT scenario, and this filter weight multiplication in the CNN scenario. Okay, so this is the basic motivation of why we are going to choose the DSP as a basic processor when we are talking about the CNN type of implementation. Okay. Now this is already written what we have mostly discussed. Why not general purpose in embedded scenario? Because embedded processors typically have a dedicated function. They are not asked to perform arbitrary functions with user-defined software. You are not going to write your own C code here. That is not the purpose of embedded processor. There is some definite purpose for which this embedded application has been developed. Okay. So making processors more specialized can bring some benefits. What are the benefits? They may consume less energy. Okay. So that they can be usable by small power or small battery resources. Okay. They may include some specialized hardware to perform operations that would be costly to perform on general purpose processor. Okay. So here we will see basically why I have talked so much about these functions, because in DSP processors we will see in general purpose processor, if you have to do it, you have to do certain steps, multiple steps to do such addition. Okay, multiply and addition. Sorry. In case of DSP-based processors, we have dedicated hardware to support these type of costly operations, and that is the main objective why we are choosing DSP processor in this machine learning scenario. Okay. So that's why the key idea is that whenever we are evaluating any processor, okay, the two things we are very much, we should need to know, we have to keep in mind. One we have already discussed, one is instruction set architecture and the processor realization. That means processor realization means other than what, okay, first we go to the instruction set architecture, then we will come to this processor realization. Okay. Instruction set architecture means is a set of basic instructions what your processor is supporting. Maybe if you remember last year we have talked about one instruction set process architecture or one instruction set computer. That means with only one set instruction also we can develop and design one computer. What will be the requirement for that? That whatever only single instruction we are choosing, that instruction is smart enough. If we arrange them properly, then we should actually implement, we should be capable enough to implement other required instructions. So from there, the concept of Turing complete, those concepts comes into picture. But the main thing is that the state of basic instructions, whatever you are defining or whatever your processor is supporting, as we have seen, that gives us the power to how much or how far we can improve some application. Or in a name, I can tell you that the type of instructions you are getting, that will actually determine how fast you can apply, how fast actually you can implement your required application. Okay, so this is a boundary between software and hardware. That means you can write multiple instructions. You want to write add, multiply, do this, do that, matrix multiplication, whatever you are writing in your code. But it doesn't mean that all these instructions will be, I mean, that they will be mapped in the same way, and it will be mapped to the actual implementation block. That is your hardware block. That is your ALU. That is your ALU. Based on what type of processor you have chosen here. Based on these instructions will be get mapped. You have seen in one instruction set computer, as we have discussed, this add, to write this add instruction, it is getting mapped to multiple number of that one instruction. Whereas if you nowadays take some ARM processor or your some Intel Pentium processor, whatever it may be, this add, it will be one shot. In a one clock cycle, they have their supported hardware and you can compute that. So based on whatever you are choosing, that will define how far or how fast you are getting your output. Okay. So based on that, you have multiple types of instruction sets. That is reduced instruction set, complex instruction set, minimal instruction set. Okay. Now reduced means you have fewer cycles. You need fewer cycles per instruction. Let's say it is a very simple example. Let's take you are trying to implement add. Add is a very simple instruction and you can implement them in a very fewer cycles. Whereas, let's say you are trying to write multiply, and this multiplication you have implemented, your hardware is implementing with repeated additions. That means whenever you are writing multiplication, you are in turn calling this smaller instructions repeatedly. That means that is not so fewer cycles. So that times number of cycles required per instruction will be more. Okay. So this is the basic difference between reduced and complex instruction set computer. Next comes the minimal instruction set computer. As the name suggests, this minimal instruction set computer is a processor architecture with a very small number of basic instruction operations and corresponding opcode. Opcode means, if you do not know, the code that is representing your operation. That means in your processor, in your basic instruction architecture, maybe 0011, that means add. I'm just giving one example. You can search with the opcode of ARM, you can get the whole list. Whatever operations ARM is supporting and what will be the map opcode itself. No need to remember anything. Just you should have the idea that whenever I am writing this do add to subtract, which opcode is getting used underline. Okay. So when we are talking about this type of minimal instruction set, basically these are the, you can say these are the optimization from both sides, reduced as well as complex. So when we have some smaller instruction set, okay, what is the advantage? When you are writing in your program add, this add is getting mapped to 0011. Now you have say a whole list of instructions, maybe L1, number of instructions you have. Number of instructions in your instruction set. Now, if you have where L is very small, to understand, to search this opcode, the search time will be very minimal. So it will be faster. Whereas you have to write more sequential dependencies when you are going to write some complex. When you have very small instruction set, that means what? You have basically written some complex instructions, and those complex instructions are actually calling in turn some basic instructions, right? Like I have given the example of multiplication, it is in turn calling addition sequentially. So repeatedly, so that is the disadvantage. That is, smaller instruction set, there should be a repeated call. On the other hand, but the search time will be minimal. So there is always some positive and negative of whatever instruction set you choose. Okay. Other than that, we have very long word instruction set. Just keep this as a moment for this moment, because we are going to discuss this in detail in our scenario. I mean, in this DSP processor, this machine learning context, we will discuss this in detail. Okay. Another one is explicitly parallel instruction. That means the instruction set that permits microprocessors to execute software instructions in parallel by using the compiler. That means there is inherent instruction level parallelism. We will also discuss this type of instruction level parallelism. And another important information, that there is one computer that is zero instruction set. That means you do not have any instructions. It basically works based on some pattern matching, and based on that also some computer can be designed. In a classical sense, that is also a full form of computer, but without proper instruction set. Okay, so this VLIW and this parallel instruction computing we will see in detail later. But the key takeaway is that the type of instruction set we are choosing, based on that, it is defining how much clock cycles we are actually using per instruction, and that for a particular application, if your application is having n number of instructions, how the total timing requirement will be there. So based on the choice of instruction set, I mean, that will affect the overall performance. I hope this part is clear. Is there any question? You can ask me now, because then we will go to the next part. Any question? So is it clear that once we are how the choices, once we make a choice of any particular instruction set, how it can affect our performance? Is it clear or not? Tell me.
Yes, ma'am.
Okay. Then this I'm just skipping because we have already discussed this one, that how this one instruction set architecture can work. We have seen this one single instruction, and based on using that, we can implement multiple instructions, and we can use in our implementation. Okay. Now you come to this embedded processing. Here we will talk about two types of processors. One is microcontroller, and then we will move to our detailed discussion of DSP. In case of microcontroller, what do you understand by microcontroller? It is a small computer on a single integrated circuit. Okay. And it is simple CPU, that means the processing unit, combined with the peripheral devices like IO, etc., and communication, embedded communication ports, etc. Like, yeah, it is written such as memories, IO devices, timers, etc. Okay. So simple microcontrollers operate on 8-bit, suitable for applications that require, we have already mentioned, a small amount of memory and simple logical functions. Okay. May consume an extremely small amount of energy, because that is our requirement when we are talking about embedded some application we are defining. We are talking about that. This is this energy is a major requirement. And in our subsequent discussions, we will see that when we are talking about this CNN and we are mapping them to embedded processor, how this energy is growing and how what are the optimizations we are, I mean, what are the steps we are taking to keep that within a particular threshold. Okay. Often include a sleep mode that reduces the power consumption to nanowatts. But this sleep mode requirement is not always suitable. This is another part we will again discuss because we need to have some design, some always on devices. Okay. So for that, how this sleep mode works and what does this mean by this sleep mode, we will talk. Next, that we have talked, maybe sorry, this is a repetition. So, embedded components such as sensor network nodes and surveillance devices can operate on small battery. Yes, we have mentioned that. And this is a boundary between general purpose processor and microcontroller. Okay. So, some of the so from this example you can see that some microcontroller when we are talking about, I mean, typical microcontrollers, they should support some block that is suitable for a particular embedded domain application. Whereas general purpose on the extreme other end, it support all type of computation. And in some cases, we have this type of the optimization between these two, like this Intel Atom. Okay, this type of in netbooks and other small mobile computers, they need the small energy without losing too much performance. So in they have some optimization in their hardware. Okay, now come to this DSP process. That is our main focus. So again, this is a DSP processor. They are some specialized computing units. And from our previous examples, what we have taken, you can understand there must be some technique by which we can actually, some dedicated hardware, we can actually efficiently implement that multiply and accumulate part. So that is written that DSP includes a hardware, a typical dedicated hardware for this. One second. This multiply accumulate unit. Okay. So we will see the structure of that unit. What we will discuss, we will talk about these variants of the architecture, addressing modes. There is one typical addressing mode that is called auto increment and bit reverse addressing, circular buffers. These three we will discuss together and we will see why they are required. Okay. We can go through this. These are very simple. With large amounts of data, data may be represented samples in time. We will concept of in this regard, we will concept about DMA, etc. here. So once we go step by step, maybe these slides, all the terms of this slide will be clear to you. Okay. So what is DSP? It is a specialized microprocessor for real-time DSP signal processing applications. Like the examples are given: filtering, FFT computation, convolution, matrix multiplication, etc. So we will be focusing here. So this is analog input when it is coming, the how general typical DSP works. That is same as what we have seen in our example also. That analog input, if it is coming from, let's say, from any sensor, some analog input in coming, that will be converted to some digital input by this ADC. Then this DSP will work on that digital input, and again some DSP will take back the output to some analog form, and it will be the analog input. Now, before we go to the details, this is a just general overview. So for this slide, especially, I request you to go through, those who do not have any idea, go through that link. There you will get the idea about this ASIC. Okay, you will get the idea about this FPGA, general purpose processor. Maybe we talked more. ASIC means application specific integrated circuit. That is the complete what I say, extreme reverse form of general purpose processor. When general purpose processor you are developing to support multiple user required, I mean, applications to implement them. In ASIC, as the name suggests, it is the application specific integrated circuit. That means it is it is specific to applications, a particular application. And based on that, you have developed one IC, that integrated circuit, the IC you have developed. It is typically will be useful only for a particular platform. Like let's consider the satellite examples or your washing machine. In both cases, these are valid. They for them, maybe in your washing machine, home smart washing machine, where you have some temperature detectors, there you have put some application specific this type of IC that will do nothing but check this temperature. Whereas in satellite communication, maybe some complex functionality, so detection or selection, there are some specific ICs present. So this is the range of embedded devices from household. So from very much critical applications like satellite, like defense, everywhere the concept is same. We have some requirement. That requirement we are putting in some small integrated circuits. We have now smart VLSI, very large scale integration of possibilities. With that, we are whatever is required for that, we are we are developing this type of app. So, if you understand this concept, you can understand that when we are talking about performance, of course, for ASIC, because that ASIC is designed, optimized for that particular for that particular operation or for that particular application. Of course, in that case, their performance will be very high. Okay. Whereas in GPP, it will be medium. We are not talking about it's very low, but an FPGA, it is having a very specific structure, that is field programmable. It is very much in between this general purpose processor and application specific integrated circuit. Go through that video and go through that audio lecture. You will find that the internal structure of FPGA. Why we tell them the in between of this GPP. There we have some components already developed. For ASIC, we are developing everything from the scratch. From the CMOS level, from the integration level, we are developing everything, keeping in mind only one application. Whereas in GPP, everything is general. In general, you can execute something. Whereas FPGA, we have some part already fabricated. Some and or some logic blocks. You will see the CLB, configurable logic blocks. Those are already there. Only you have to make a few connections to implement some your application. So that is in between this ASIC and FPGA. So if you understand this, what is their purpose, you can of course understand that performance also will be high. Not as high as ASIC and not as low as medium. Okay. Similarly, the flexibility on the other hand. Flexibility for ASIC, it will be very low. Why? Because it is developed for only for one particular application, nothing else. So it is not at all flexible. Okay. Whereas in GPP, you can see the flexibility is very high. Okay. In fact, in FPGA also it is showing high, but of course there are some implementation difficulties. When you go through that lecture, you will understand the implementation way. GPP implementation, you all do the C coding, you execute. Steps you have to follow the FPGA implementation, and that is a bit costly. Not so, not so easy. That's why it is shown here. On the other hand, if you go to this development time, it is long, because for this one application, you are doing everything. You are first modeling it, then implementing it, then fabricating it. So the whole development time is very high. Whereas FPGA, some part is already developed, and on top of that, you are actually implementing your application only. So only the application level implementation you are doing there. So that's why this is medium. Whereas in GPP, this is very short. That's why if you go through that lecture, you will get how actually we are implementing in FPGA part. And then you can do, you no need to read this slide, I think, after that. After that, you will, your own, you can actually write this table. No need to go through the slide. So then you can understand the development time of GPU. You have already have the GPP. You are just writing some. You are opening some editor. You are writing some code. So development time is very low, very short. Same as age. Okay, we will come to here because we will focus here. Similarly, the flexibility we have talked about. We have talked about performance. Now the power consumption. Now this is very important part. This is very low, low, medium, and low medium. Okay. So as you understand, since we are talking about a particular application, and that way we have designed our chip, designed our IC. Of course, the power consumption will be very low because we have only supporting one application. Whereas if this GPP works on some predefined structure, on that predefined structure, we are developing our application. We are defining our application blocks. So that's why the power consumption is not so, it is medium, or in this way you can say among these four, you can say it is high. On then you are talking about FPGA, there some part is already optimized. On top of that, you are developing your application, hence it is low. And then come to this DSP part. Okay. So in DSP part, this is telling that this performance is medium high. What it tells that is it is medium. It is like GPP, but it is very much towards like FPGA. That means it is developed kept in keeping in mind the concept of power consumption, because it should be used, it will be used in some low power range. It will be used for some low power range applications. And then the flexibility means it is not only this type of signal processing applications. Many more applications can be supported. That's why flexibility is there. But for particular some typical type of applications, it works better. And development time, it is again very small, short, because it is very much same as GPP. When you are coding them, you can actually use those same concepts. So no need to do those connections as we are making in FPGA, or no need to do starting from all modeling, implementation to fabrication, all the steps you no need to follow when we are talking about when we are here in this aspect. So this is why we are choosing DSP, because for a particular application it works better. Whereas if you have to extend that application a bit, you will get some flexibility. It is as per whatever for few applications, whatever power consumption you can support, it is as per that, and the development time is also short. So that way DSP is, as we mentioned, this is an application specific processor, and it is suitable for those applications. And we are here talking about this type of we have got, and since DSP is quite well worked, it is quite suitable for this signal processing algorithms, and we have actually mapped our CNN steps, how we are multiplying this weights with the input feature maps very well with this FFT computation or signal processing algorithmic steps. DSP is a suitable choice for us. Okay. Now we will these DSP features we will see one by one. The first one is Harvard architecture. What does it mean? This Harvard architecture looks like this. Physically separate memories and paths for instruction and data. As I mentioned in the first slide, that we have some memory. Memory means nothing but storage. My final idea is from this storage, some data will go to my CPU, some instruction will go to my CPU, and the computation will take place. In case of Harvard architecture, this is separate. So what is the advantage? Can you tell me what is the advantage? It's very easy to understand. Anyone? Anybody? Are you listening? First of all.
Ma'am?
Yes, ma'am. Yes, ma'am.
Yes. Okay. So tell me, what may be the one second, sorry. What happened? Yeah. This one. What may be the advantage?
Ma'am, parallelly data memory and program memory can be accessed.
Very good. What else?
Instruction level parallelism can be achieved so that no number of instructions will be executed per se.
Okay, yes, parallelism is one important factor. That's why someone knew when this Harvard came into picture. What else? What may be the other case? Someone who has done that security related requirement. Do you think this is secure or insecure? With the reason with why I'm asking, my question is not clear. That just think in this way. Anybody want to tell anything? No, right?
I think this is secure, ma'am, because like the data memory can be protected more. If both
Yes.
are in the same place, like the program memory is accessed frequently, rather like more frequently than data memory. If we have to like create that security for the whole memory case, then the performance will become slower. Then
Yes, one thing that see performance and parallelization, whatever you have told, it is goes hand to hand, right? You are improving the some scope of parallelism means you are in turn improving the performance. That is one thing, and you are correct that it is more secure. Why? Because if somebody is getting access, is there different types of attack maybe in our security space class we have discussed. If someone is actually poisoning or attacking this program memory or maybe data memory, whatever it may be, it is not getting any direct hold in this program. So that means it may happen. It is the adversary is corrupting some amount of data. But for other instructions, those are executing fine. Or it is corrupting some single or multiple instructions. That's all. It is not affecting your whole data memory. So that way, this architecture is more. It obviously gives. It is a more scope of parallelization, more scope of security, and the simple thing is that about the performance. If you forget for the timing for about parallelization also, if you have to store the data and instructions together, that means you have instruction maybe data, then instruction and so on. That way it will be huge, one memory will be huge. So the search time for any single instruction or any single data search, the time will be more. Of course, that way whatever you have answered, that is correct. That is a connective answer, that if we go for the separate memory, we can increase the chance of parallel. Okay. So I think it is clear why this Harvard architecture came into picture. Okay. Then the second feature of DSP. Okay, Harvard architecture, then dedicated this. I mean, single cycle multiply accumulate instruction. Okay, that means, as you remember, we have discussed repeatedly. If we go back to this slide, that this multiply and accumulate or multiply and add. This is the requirement for DSP. DSP. This is a requirement for our CNN, and we are going to achieve this. We have some benefits when we're using this DSP processor. We have this type of single cycle MAC unit. That means your processor is it's supporting a particular MAC unit like this. In a single execution cycle, you are doing this multiply and accumulate. You can see this. You have this AI and Xi. Maybe you first A0 and X0 you are storing, then A1 and X1 you are multiplying. Then you are adding this A1 and X1 and storing that this addition plus multiplication in a particular register. So that means if you are trying to compute this multiply and accumulate, you can compute that this sum as a just in n cycles, because at each cycle you are actually getting the support of both multiplication and addition. So this is, and now you understand that this also can be heavily used in our conjugation layer, and that way, that's why this DSP, these processes, this type of processes, they are basically meaningful whenever we are talking about this CNN improvement. Basically, you know what? One thing I must say, nowadays you can see everywhere there is a boom of this machine learning. Okay, everyone is trying to do or do some course or some study on this machine learning. But when we talk about hardware, people just say, no, okay, that is in the back end. But machine learning would never have been machine learning. I mean, this boom would never have came whether this machine learning algorithm they had not got this hardware support, because hardware was there, and that hardware mapping was done efficiently. That's why this machine learning algorithms, those can, I mean, people got access and people could have implemented in this wise way. And with this, I mean, they together, this hardware support and this machine learning together develop the flourish this subject, this applications of machine learning. So this part is very, I think, important. I mean, this is a hardware contribution to machine learning that we most of the times we do not acknowledge or we do not discuss much. Okay. Next, another thing is that single instruction, multiple data. Okay, this is this SIMD. SIMD technique, as the name suggests, I think you already understand that you have some instruction pool. Okay, from there you are taking one instruction, but you are applying them to this physical. This PU is the physical unit. Okay, and this physical unit is taking this instruction and the same multiple data from this data pool. That means same instruction coming from this instruction pool is getting applied to multiple data, and then together it is another sort of parallelism. Together this data level parallelism, we can say, and in parallel you are getting the output. So if you think in our context, in CNN context, of course, you are basically doing the same instruction, multiply and add, and add the same instruction, only the multiple data. So your this weight is changing, this the feature map input is changing, weight coming from your filter is changing, maybe the bias is changing, but the instruction, same instruction you are applying on this multiple data. So SIMD is very effective to improve the performance of your CNN. Okay. Next comes the this VLIW, very long instruction word. Now this VLIW, it is quite similar concept, but you can see first you see this instruction structure. I think you remember we have skipped this part when we discussed initially. This VLI instruction looks like this. You have your instruction word means maybe you can take this as one instruction. This is one instruction. But you have some huge hardware support in such a way that the part of this instruction, this part you are actually mapping to some adder. This part you are you are mapping to some division block. This part you are mapping to some other this, and this is some multiplication block. So this way you have one single instruction word. That means this single instruction getting executed in a single instruction cycle. But that instruction, this is called instruction level parallelism again. By executing instructions without any dependencies. If they do not have dependency, you can form that instruction word, very large, long instruction, large instruction, and you can actually apply them parallelly. But of course, for that, I think no need to say that you need to have the support of this, hardware. Without this hardware support, you do not have this hardware support, you actually cannot we cannot actually form this very long instruction one. In spite of the fact we form this VLIW instruction, it can't be actually executed in parallel. So for that, this VLIW instruction, we need to have this variant of hardware blocks in our processor, that DSP has some variant of blocks as per requirement, and in those blocks we can actually map the parts of instructions. Here one instruction, we are dividing them into parts and we are in parallel executing them. So this is the concept of very long instruction. This is another feature. So we have talked about this Howard architecture, MAC unit, SIMD and very long instruction. Then we will come to this pipelining part. Before that, there is one comparison, sys, RISC and VLIW. We talked about sys, RISC before and this VLIW. Just you can go through this tape. Okay, let me just, I want to explain this one. I think previous ones are self-explanatory, you can understand. If you go through it, if you require, I can explain that later. But one thing, how you are representing these instructions. In case of sys, you can see this is a very important thing, that instruction size that varies. That means this is one complex instruction, this is one complex instruction, and they are in turn, the smaller blocks are, maybe you can think as some smaller instructions. Now, how many number of this type of smaller instructions you are actually calling, or what I should not say calling, you are clubbing inside this sys, that varies. In case of RISC, it is very fixed because you have basically those are very regular. In case of VLIW, it is again regular, but that is the number of how many these blocks you are calling or how many smaller instructions you are calling. Those are numbers are very large. So I think this is very important concept, that when we talk about sys, always it is not that all instruction size is the same. It may vary, but whereas we talk about this RISC and VLIW, etc., the instructions are of same size. Okay, so now how do we offer parallelism? We talked about that parallelism. You all actually mentioned that parallelism can help us. So we talked about this kind of instruction level parallelism. Instruction level parallelism means we have talked about this VLIW. We talked about this SIMD also, that is also multiple data level parallelism. We have multi-core architectures. That is very straightforward to understand. If I have multiple cores, I can actually, if I have, let's say, 5 additions I have to perform, and I have maybe 8 cores, then I will just send them to this multiple cores, and at a shot I will get the output of this 5 additions, provided they are independent. It is very important. There is another course of parallel algorithm or something similar to that, you can see. It is one important takeaway is that you cannot always, if you think and support hardware, then also you cannot improve the performance, because you cannot do the parallelism itself. Parallelism entirely depends on the algorithm what you are actually writing, what the algorithm you are implementing. Because if you can make any if you are actually considering any dependency, in that case you cannot exploit always the what to say, the help of parallelism. In spite of the fact maybe you have multiple cores, then also you may not take the help of those multiple cores if these additions are independent. If these additions are dependent. So independence or dependence, those are very, in your instruction steps, those are very important decisive factor how much parallelism actually you can exploit. Okay. Next one is, so these two I think you understand what to do in this parallelism. Next comes this hardware parallelism, that is the pipelining. Okay. So pipelining in DSP requires these fetch, decode, execute code. But this is, we will come back to this slide. First, we need to understand from the basic, what do we understand by these codes? For that, just think about this type of processor architecture. So what we have mentioned that whenever we are going to execute instruction, let's say add, then subtraction. Maybe this is my first instruction in my whatever code I have written, C code, then subtraction, then number 3, multiplication. Okay. So that means we have some op code related to op add. Let's say I'm naming that op add. This is op sub. Sorry. And this is op multiplication. So that means this is my memory. This op add, it is stored somewhere here. Somewhere here. Then this is my op sub, it is stored somewhere here. This is my op m, it is stored somewhere here. That means in clear form, this is my memory. Somewhere it is storing my op add. Somewhere it is storing op s. Memory means I'm telling it as instruction memory. Okay, instruction memory. And this is op m. Now I have a PC. PC, this is a program counter or register. Okay. By the way, if someone is, wants to read this in detail, and if I have already, I will show you where is this one? The book name. Here, this book is given in reference also. You can just refer to that book. Okay. This part will be very much clear. It is nicely written there. So this PC, it is a register. Register means it is holding that what instruction I am going to execute. First, I have written add. So this PC is actually holding the instruction for this instruction add. Okay. Sorry, PC is holding the address where this first instruction is residing. Okay. Let's say if this is at first it is pointing to this instruction, this memory address it is holding. In this memory, we are having the opcode instruction code for this addition. Addition means what? It is holding and what to do. That means it looks like this. Some opcode that is telling whether you are going to do addition, subtraction, etc. or not. Next, some source values from where you will fetch the values. That means maybe some register values R1, R2. And then you have computed add, fine. Where you will store that? Some destination R3, maybe the destination. This is your destination D. Okay. So in these registers are holding the data for your addition. If this is the case, this PC will point to this memory. So memory is giving this address, and this opcode you can see here from these registers, it is getting passed to this ALU in it. That means ALU from this opcode part, it will understand, okay, now I will do the addition. And it will also, the inputs will go to from this instruction. You can see here these paths. It is fetching the registers from where the value will be passed to this ALU part. That means value is coming here, instruction what to do is coming here, then ALU is generating the data. This is result is coming here. Now what you have to do, this result you have to store back to this R3, some register 3. Okay. Or it may happen you have to store it to some memory block. If that you are storing that to some memory, the data memory, that means this result will go from here and you have to store that to that data memory, and that data memory, the address where you will store that value, that will be coming from here, from this destination part of your instruction code. If not, this value will it will go back. You can see here, there is a path, there is a back path. Okay. This path will go and it will store here, store the value back to your register. So this is the flow. Whenever your hardware, your CPU is actually executing any instruction, it is basically checking what you have written, what I will do, from where I will fetch the data and where I will send the data. Based on your instruction, is getting mapped to some 10 values here. That is your instruction code. That instructions code is residing in your instruction memory, and from this instruction memory, this instruction is going to your register file, to your ALU, to your memory, etc. So this is the step. Okay. So these steps, in case of pipelining, for this instruction execution steps, are divided into 5 steps. One is instruction fetch, one is instruction decode. Instruction fetch means you are fetching the instruction, these 10 values from your instruction memory. That is holding your opcode, holding the source address, holding the destination address, etc. So that is the instruction fetch. Then it is the instruction decode. Instruction decode means it is telling you what to do, what I will do, whether I will store the data back, I will do whether I will fetch the data from some register, or what I will I'm having some data, should I sign extend that, what I will do. So based on that, this instruction decode step is there, and based on that, the next sequence, the next part comes into picture. This is the ALU part. It is accordingly it works. It has to do this addition, subtraction, it will do that. Okay. Then from there, memory access. That means I have the result now. From my ALU output, I got the result. Now, should I store that to memory? If there is a memory access requirement, the value will be stored to this memory. If not, the value will be passed. See, we are passing this value to the next stage. And then in this case, this is called write back. Okay. This is writing back this value. You can see here, this value is going on here, and it is going back to register file. So these are the, whenever we are, processing unit is executing any instruction, these are 5 stages. Is it clear? We have not talked about this next, zero, etc. This is for branch. Like when you write this, I have whatever I have written some simple instructions. Now, if you write, let's say your add result is C is equal to A plus B. Okay, C is equal to A plus B. Now you are writing if C greater than 0, do some instruction. Maybe you are again doing some multiplication. Okay. Now this if instruction, that is called some branching instruction. So here you are checking whether this value is 0 or not. If it is true, then there will be some branch taken, branching steps will be there. If there is no branching, it is not 0, then it will go to some next sequence. That means it will go to some next instruction present, stored in your instruction memory. And if it is making any jump, maybe it will make a jump based on whatever you have stored in your instruction memory. So this is the execution. This is the basic idea of how an instruction gets executed. Okay. So I hope these 5 stages are clear: instruction fetch, instruction decode, instruction execute, memory access, and write back. And when we are talking about pipelining, this is nothing but, again, apply some parallelism on this instruction execution steps. See here you have this 5. Sometimes we divide this instruction execution stages in 5 stages. That's why this is called 5-stage pipelining. Sometimes we have 3-stage pipeline. When we have divided this, maybe that it may happen for simpler this DSP applications, or this type of CNN applications. This instruction decoding, because there is not very much huge types of instructions. So this decoding is not so important. We know there is particular type of instruction. So instruction, decoding, and execution, those are fused. So that time we get some this type of 3-stage or 4-stage pipeline. This is a more generalized version, but what is the basic idea? You can see whenever for a particular instruction, if this is my instruction 1, instruction 2, and so on, maybe it is instruction n, then we have actually, whenever we are doing this instruction fetch, the first one we cannot do anything, this is empty. But for the first instruction, when we are doing instruction decode, these parts, this instruction fetch, this hardware is basically was sitting idle. If I was just going by instruction, if I had a plan that okay, I will first complete all the 5 stages of this instruction 1, then I will go to instruction 2. If that is the case, when I am in the instruction decode stage of this first instruction, basically my instruction fetch, these hardware, whatever I had here, this part was sitting idle. Now we are not allowing that. We are arranging this instruction fetch along with of this instruction 2, along with this instruction decode fetch of instruction 1, so that they can be executed in parallel. Okay. Similarly, as we proceed, we can actually set up this type of parallelism for execution of instruction 1, instruction decode of instruction 2, and instruction fetch for instruction 3, and so on. Okay, so this is the basic concept of pipeline, and you can clearly see the advantage. So at a particular time, when initially, if we had to complete this, if we consider this as one cycle, so initially, if we were not using any pipelining, any parallelism in this manner, instruction, this is also another type of instruction level parallelism. We were used to do it the whole instruction execution up to 1, 2, 3, 4, maybe 5. We had to take this 5 into 5 cycles. 5 into 5 cycles. But now we are finishing this 1, 2, 3, 4, 5. This is much reduced cycles. We are actually completing this 1, 2, 3, 4, 5, 6, 7, 8, 9. So we are finishing this in 9 cycles. Now after parallelism, we are actually saving this much of cycles. This is I should write that without parallelism, and with parallelism we are actually 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 cycles. I think it is clear, the pipelining advantage. Yes,
Yes,
no,
ma'am.
clear, right?
Yes, ma'am.
So just when we go back to DSP, we have this fetch, decode, and execute. So some of these stages what we mentioned, those are fused, and parallelism is basically 3 pipeline stage parallelism. Okay, see, we have considered 3 pipeline stages, and there we have implemented the pipeline. But if you go for high-end processor, high-end systems, we generally see this kind of 5-stage pipeline. So whenever we are mentioning any kind of pipeline, it is important to tell what stage of pipeline we are actually considering, because based on the stages you are choosing, it may happen that will actually define how much gain you are actually expecting from that pipeline. Okay. Now this is a simple thing. Okay, whatever gain we have discussed, whatever gain we can actually achieve through this pipeline. But there are some problems, hazards associated with these pipelines also. What are they? We can take these examples and then that will help you to understand. Okay. Let's say you are considering these instructions. You have written these instructions. This is load word LW. If one of you do not know, this is load word. Load word. It is S0. You are writing. You are doing some operation and you are writing that value to S0. Okay. Now this, if you are directly implementing this 5-stage pipeline, then you have this instruction fetch, decode, execute, memory write back, and register write back. Okay. So this is if it is in register 0 or memory 0, let's say it is in register 0. So you are writing this S0 value to this 5th cycle. Okay. In the next instruction is add S3, S0 and S4. That means you are adding this S0 and S4 values and you are storing them back to S3. If this is the case, now this is your instruction 1 and this is your instruction 2. Okay. Sorry. So if you, as general pipelining strategy, you have just started it from here. You have fetched the instruction. You have checked. Okay. You have to do that addition implementation. Then you have done this decoding that. From their decoding idea you have got the idea that okay, I will fetch the value from S4 and I will fetch the value from S0 and they will then in the execution phase, that means here they will be added. But when you are coming to this execution phase, this data, this updated S0 value that you were actually expecting as the outcome of this instruction 1, that is not ready yet. That means if you are now just directly following this type of pipelining steps, that is this traditional pipelining stage, without any added support, then what will happen? This execution, whatever you will be doing, that will not be done on some updated value. So updated S0 value is not updated S0 value is not ready yet. Is not ready yet. That means you are doing this addition of some old value. In spite of the fact the way you are writing, you are thinking that okay, I will load some word in this S0 and on that S0 value I will be doing that addition. But actually speaking, when that execution is taking place in your pipeline processor, if this data hazard solutions or there is a no check that whether the data, there is a possibility of data hazard or not, then this output will be wrong. The instruction 2 output will be wrong because you have your processor has actually computed that on some old value. Okay. So for that, this situation it is called data hazard. Okay. And for that, what you have to do? Okay. The solutions we will come later. First check another example. What is the problem? This is for data hazard. Okay. Now come to this control hazard. Okay. Again, you draw the 5-stage pipeline. You are telling here BEQ. That means BEQ means branch if equal. Okay. Branch if equal. Okay. So if you are actually comparing these two T0 and T1 register values, and if they are equal, then your program should branch to this level L1. And in this level L1, something is written that there will be some subtraction, etc. Now you have done, if you are doing this instruction, executing this instruction separately, this is fine. You are first checking this equality check, and then if it is 0, you are doing something. If it is 1, you are doing something. But the problem is when you are feeding them to your pipeline. So this is something like this: 1, 2, 3, 4, 5. So again, instruction fetch, decode, execute, and then memory write back and register write back. So first branch is equal, that execution has taken place, and you have got the output 1 or 0. Okay. After that, maybe it is finally this. Memory and register write back. Okay. So after execution of this comparison, equality check means in your ALU, now think in terms of the hardware, that in your hardware you have some equality check module. That equality check in your ALU that has checked whether it is 0 or not, or equal or not. Based on 1 or 0, you are ready to do that jump to the step. Let's say if it is 1. Okay. But before that, in instruction 1, this is instruction 2, according to your how you have arranged your instruction in your instruction memory, this is your next instruction. So that is already entered in your pipeline phase. That means now, in spite of the fact you have got some result 1 and you have to jump to this L1, that time there is no point executing this instruction. But still this instruction, it already entered to your pipeline cycle. So these are something what we can tell, that this is some wastage of resources, but you are just executing some unnecessary instructions. Okay. So when we do not know that which instruction we need to be executed next, then this part is called the control hazard. Okay. So the first one, before that, when your data is not ready yet, here, when your data is not ready yet, updated value is not ready yet, this is called data hazard. And when it is related to your loop handling, it is related to your control step, where which instruction you will consider next, that comes under your control hazard. Now, frankly speaking, this data hazard, you can take this example also you can by your hand, you write and you can check how this control hazard is also happening here. And there are some typical solutions. One is forwarding or bypassing. One is stalling. Now, stalling means maybe you are giving some extra delay. You are stalling your instruction for a bit. Or forwarding means maybe your data, you can see here, in spite of the fact this data execution output, it is getting written in this S0 register in this step, 5th step. I am talking about the data hazard part. It is getting written back in this register in the 5th step, but this data is ready in this 3rd cycle, cycle 3. So if you need that this in your next execution, then you just directly pass this data on. And so for that, to pass that on, you need to have some extra circuit that will detect whether there is any possibility of data hazard or not. And if there is any possibility of data hazard, you have to bypass or forward. That is the concept of forwarding. You have to forward that data from this after this execution phase directly to the next execution phase. So there will be some extra path given, so this data can be forwarded. Or what is the other option? That when you have getting the idea, there is a hazard detection circuit in your pipeline step. If it is detecting, okay, there is a possibility of hazard, then the next possible solution is give some stalls here. That means you just do not do anything for these steps. Do not do this execution for these 2 steps. Put some delay for these 2 cycles. and after that you do this execution. Okay. Now you can understand these are the two solutions for this forwarding and stalling. You can see here with this example, if you do by your own, you will get a better understanding. When this data is required here for this execution, this data is required here, but you are supposed to get the final data in this step. So there is a forwarded path. Okay. And the stalling is not shown here because that when we generally do the stalling, that is we have to add some extra delay circuit for that, and you are losing some cycles. When you are actually stalling, you are losing some cycles. In that way, forwarding circuit is forwarding or bypassing the data as much preferred. But of course, to implement that forwarding, it has some, I mean, it is costly in terms of implementation rather than implementing this delay set. Okay. It may not work always. Always you may not forward. So here one example is given that even in forwarding, there is some problem with this data dependency. So that's why I was mentioning that, okay, yes. Okay, this is the solution for branching. I will come later. So the thing is that what the key point is, but it is always not. I mean, what to say? It is not confirming that still then you cannot have any hazard. So that's why when we are designing, we have some. We should have in our designing. In modern processors, they have some hazard detection circuits, hazard detection units, and based on that, some supporting units are there for this forwarding, and they see here for this forwarding or for this stalling. Okay, and what about this? This is all about what we talk about data hazard, about that control hazard that I mentioned in this example. That we do not know which instruction needs to be executed. So this, in such scenario, the direct solution is we assume the branch is not taken, and based on that we load the next instruction, and if there is a branch taken condition, then we just remove the effects of the previous instruction execution. That means we do not consider that those instructions we have executed, those are wastage, but still we have to allow this type of wastage, because if you write any application, you can observe that most of the cases we write sequential instructions, and in some cases this branching is there. So based on the application, if you have a very huge percentage of branching instruction in your code, then this pipelining may not be effective. But in general, for general applications, most of the instructions are sequential. In that case, the branching will help. So all this, why I'm telling this type of instruction parallelism, what we have talked about, this CISC instruction, we have talked about this VLIW, we talked about this pipelining, that is hardware parallelism, and another one is the subword parallelism. That means this is very important. We will talk a bit later, the subword and superscalar, and this is very related to our CNN application also, especially when we talk about images. So we will come to this, but all this pipelining strategies, all this instruction parallelism, VLW, we actually apply when we take our CNN module, when we consider our convolution multiplication. We basically break those instructions in this form so that we can execute we can exploit some VLI AEW feature. We can actually support some pipelining. So all in this way we will see in our coming classes that there will be some different levels of optimizations we will provide. We will provide some algorithm level optimization. We will provide some hardware level optimization. So in some of the algorithmic level optimization, we modify the steps in such a way that we can exploit more about these parallelism techniques. We can exploit more about this real IW. We can exploit more about this pipelining, etc. Okay. So, is there any question on this pipelining part? Is it clear how the pipeline can be given? What are the advantages and what may be the limitations, and what and which steps for which types of hazard we should be careful? Is it clear?
Yes, ma'am.
All of you? Because next week there will be one class test. So at least ask me if you have any doubt. Next, come to this part. So CISC, we know that complex instructions, that means we are using some rather not so complex or simpler instructions within CISC. So this is one sort of parallelism. But this CISC, for to implement this CISC type of approach, we need to have multiple ALUs. If you do not have the hardware support, we can never think about any kind of improvement. And another is that subvert parallelism. Subvert means, this is very important when we will be talking about this channel handling in our CNN scenario. So what happens in here, it is written many embedded applications. Actually, it is important for our our application. You can think about the images, the color pixels. Okay, so they are represented by this RGB format and 3 bytes, 888. But whereas we are having in some cases 64-bit ALU, that means all the processing can be done with this 64-bit. So that means you have this RGB8 or RGB. Okay. So when you are just processing these channels separately, you are just processing for B or G or R, whatever it may be, you are effectively processing for 8-bit data. Whereas you are using this 64-bit ALU, that means you have maybe one adder or multiplier that can process 64-bit data. 64-bit data. 2 inputs that can take as of 64-bit. So subvert parallelism says fuse them together. So whenever you are executing, you are giving input to your adder block, you make a 64-bit input, and for them one will come from this R value, one will come from this Z, and one will come from this B value, B part or B channel, and together process them. So in that way, these type of parallelism, this is called subvert parallelism. This is something similar to VLIW, but in VLIW case, we are considering that instructions under that VLIW instruction, log instruction one, we have multiple different types of instructions. Here, we are basically making it together the input of your ALU. Together we are processing, but for us, these 8-bit separate values are meaningful. But we are fusing them together and we are processing them with our 64-bit ALU. Okay. That means this is the main idea why ALU is divided into narrower slices, enabling simultaneous arithmetic or logical operations on smaller words. So that means though you are processing 64-bit together, basically you are applying supporting parallelism on this inner 8-bit. Okay, this is called subvert parallelism. And it's shown the same thing. Okay, and that the superscalar, and it is very superscalar. Sometimes it is like out of order execution other than VLIW. VLIW we have discussed. Along with that, we have one extra point, that is out of order execution. What does it mean? Let's say you have this type of instruction: add C is equal to A plus B, add what is it? C2 is equal to C1 plus C2, multiply some B plus C. Now if you observe, you can see these two, they have some dependency. Until you are getting proper value of C1, you cannot feed them to some this type of subword parallelism or this type of some parallelizing technique. So do some out of word execution. So you actually merge these two, this 1 and 3. And together you process them, you feed them in some subword parallelism. And then you process this one. So this is some kind of out of, you are not following exactly your instruction orders. You are actually, there are smart hardware, they can actually give, that will not change the behavior of your program, but that will support that this type of out of order execution to exploit the possibility of parallelism more. Okay. So these are few words about parallelism. You can ask me if you have any doubts, or maybe next day also you can come with the questions, because then the next we have discussed so far about the DSP features. Okay, go back. Yes, we have discussed up to so far. We have discussed Harvard architecture. We have discussed this Mac units. We have discussed VLIW and CIMD, and then we have discussed about pipeline. Next day we will discuss about these two, cache and DMA. Okay. So today I'm not starting them. So I think that's all for today. You can ask me the questions, whatever doubts you have.
Ma'am, which kind of microcontroller is usually used for embedded machine learning, ma'am? Currently in the industry.
Currently in the industry, I'm telling this DSP processor is one of the solutions. That's why you can see this paper, what we are referring, it is a very recent paper. Okay, this is the paper. Okay, acoustic. This is, you can see the whole year. This is published in August 2020, and this is the solid state study is a very top notch. I mean, when of this implementation. So when we are talking, it will not only DSP processor, I should not say in this way, but when you are thinking about this CNN concept, then we are telling that DSP is meaningful. Okay. If we are thinking about some other, we have actually next day you will, tomorrow there will be a demo for you. There you will see some other that will be some simpler example. There you will be seeing that we are not using the DSP, we will be using some Arduino framework. You will be having your first assignment based on that. There you will be seeing that you use that this OK Google concept, right? That, or Alexa, your voice modulation. There also you will see, I mean, you will do that by your own. One demo will be shown that is based on some Arduino framework, and that microcontroller is actually different. That is not DSP. So it is based on your application. We choose this underlying processes. And as we proceed with some other examples, you will see the platforms will also change. Okay.
Ma'am, another question. Ma'am, can the DSPIC33 series of PIC microcontrollers be used for voice recognition, ma'am?
Now you tell me this answer. When you are doing this voice recognition, what type of you are voice? That means you are telling ML based voice recognition or some smart technology. You are thinking, right? When you are
yes, ma'am.
So if you are thinking, then you think about the machine learning algorithm, right?
Okay,
What we are telling here, if you are talking about this machine learning algorithm based on this CNN, this convolution, where you have to do huge type of multiplication, matrix multiplication, if you have to do something like that, then of course your DSP type of processor will be meaningful. Okay. If you are thinking some other kind of machine learning algorithm, then your processor may change. You may not need DSP in that way. Simply other type of microcontroller will suffice. We'll see tomorrow also.
Okay, ma'am. Thank you.
Anything else? if there is nothing, we can wrap up the class. You can leave. Tomorrow we will begin this test. Okay.
And when
Thank
will
you.
be the test?
Yeah. Yeah.
When will be the test?
Test will be next Tuesday. Okay. So what we will plan, we have to take 3 class tests, I think, 3 tests, I think. If we take go for in that midterm and some form, I think there was some circular that we have to take at least 3 tests, 3 tests. So what I am planning that starting of each month, like September 1st week, we will take 1, October 1st week, we will take 1, and at the end of this is now November 2nd week, or that is the last class around that time, that will take another we will take another test. So there will be 3 tests and some assignment submission. So assignment will be based on your this type of demo. You will do it your own, and then that output you will submit. Okay.
Thank
So
you.
maybe next Tuesday will be your test. Thank you. You may leave the call.
Thank you.